The development of a single-gain tuning regulator, or SGTR, is presented for stable linear time invariant systems, with a focus on output regulation. Building upon the original tuning regulator concept introduced by E.J. Davison in 1976, this novel approach retains inherent data-driven properties and guarantees closed-loop stability when tuned online. Notably, the SGTR improves upon the original design in two significant ways. Firstly, it relies solely on open-loop frequency response data from the plant, eliminating the need for additional information. Secondly, it can be tuned online by adjusting a single scalar gain, simplifying the tuning process. Furthermore, the SGTR comes with a stability certificate, ensuring that the dominant closed-loop eigenvalues have a stability margin of O, thereby guaranteeing stable performance. The efficacy of the proposed method is demonstrated through a problem of disturbance rejection for the 4-tank control process, showcasing its potential in real-world applications. This section of the research paper delves into the issue of error feedback output regulation for a stable but unknown system, focusing on the multivariable tuning regulator proposed by E.J. Davison. The paper commences with an introduction to the finite-dimensional causal LTI plant and its associated exosystem, which generates exogenous input signals that need to be rejected or tracked. It then formulates the error feedback output regulation problem as a design challenge for a dynamic controller that processes the error signal and produces control inputs, ensuring internal exponential stability and regulation of the closed-loop system. The paper underscores the importance of the non-resonance condition, which states that the transmission zeros of the plant must be disjoint from the poles of the servocompensator. This condition is necessary and sufficient for the existence of a stabilizing compensator solving the regulation problem. Davison's tuning regulator is introduced as a special case of the design approach, inspired by classical online tuning approaches for integral controllers. The characteristics of this approach include requiring only the DC gain of the open-loop plant, systematically achieving a stable closed-loop system through the tuning of a single scalar parameter, and the simplicity and practicality of the control implementation. The paper then presents the multivariable tuning regulator proposed by Davison, which aims to mirror these characteristics in the MIMO LTI case for more general reference, disturbance signals generated by the exosystem. The design procedure involves defining the exogenous input signals and requiring an integral controller with specific properties. The paper concludes by emphasizing the need for satisfactory performance, which may require additional stabilizing precompensation before tuning the integral loop. The proposed single-gain tuning regulator, SGTR, aims to address the complexities and stability issues present in its predecessor, the original tuning regulator. It simplifies the implementation process and provides essential stability margin information. By reducing the number of online tuning parameters to a single scalar greater than 0, the SGTR facilitates a direct mapping from open-loop plant frequency response data to fixed controller gains. This design objective is crucial for enhancing the efficiency and reliability of multivariable control systems. In terms of stability analysis, the closed-loop system with the SGTR is evaluated for low-gain Hurwitz stability. This requires the dominant eigenvalue of the closed-loop matrix A to be O, away from the imaginary axis for sufficiently small values of. A pivotal result in this context is the development of the steady-state loop gain, SSLG, operator L, which plays a key role in characterizing the low-gain Hurwitz stability of the closed-loop system. The SSLG operator serves as a critical tool for analyzing the stability properties of the SGTR, providing valuable insights into its performance and potential limitations. Overall, the SGTR offers a promising solution to simplify and improve the tuning process for multivariable control systems. By leveraging the SSLG operator and focusing on low-gain Hurwitz stability, the SGTR has the potential to significantly enhance the efficiency, reliability, and overall performance of these systems. The authors delve into the analysis of the closed-loop system matrix A, in terms of its low-gain Hurwitz stability. They introduce a reduction lemma that allows them to focus on the low-gain stability of the matrix ARD equals GL, F. The authors also define low-gain stabilizability for a pair, A, B, which is characterized by the existence of a feedback K such that a BK is low-gain Hurwitz stable. The authors then prove that the pair G is low-gain stabilizable due to its controllability and the fact that all eigenvalues of lie on the imaginary axis. This leads to the conclusion that there always exists a Z in F such that GZ is low-gain Hurwitz stable. The authors summarize this in Lemma 5, stating that if Z equals L, F is solvable for F in F, then F solves the SGTR problem. The authors proceed to analyze the computation of the controller gain F by solving the operator equation Z equals L, F. For F, they establish that the SSLG operator L is surjective if and only if condition 7 holds, and that L is invertible if R equals M. This result is encapsulated in proposition 1. Finally, the authors present theorem 1, which states that problem 1 is solvable if condition 7 holds. The authors also highlight that the SSLG operator L depends only on the frequency response samples, a fact they will demonstrate in subsequent sections. A novel approach to designing a single-gain tuning regulator for low-gain stabilizable systems is presented, comprising a 3-step implementation procedure. The methodology begins with the definition of the SSLG operator L, a linear map utilized to solve for the desired feedback gain matrix F. This is achieved through eigendecomposition of the system matrix and application of the final value theorem from Laplace transform theory, yielding an expression for L, F, involving a sum over residues at the poles of the system's transfer function and its conjugates. The design procedure commences with the creation of a low-dimensional stabilizable system Z2F, ensuring the system matrix GZ is low-gain Hurwitz stable. This is accomplished by first designing a low-gain Hurwitz stable system Z2F and then setting Z equals Z, IR. Subsequently, the linear matrix equation L, F, equals Z, is solved for F, leveraging the surjectivity of L. The solution can be computed using a vectorized linear system. Finally, the tuning parameter greater than 0 is adjusted for optimal performance, guaranteeing internal exponential stability of the closed-loop system for all within a specified range. This framework draws upon techniques from control theory, signal processing, and complex analysis, providing a comprehensive mathematical foundation for the design of single-gain tuning regulators. The application of the single-gain tuning regulator, SGTR, to a 4-tank process control problem is discussed in this section, with a comparison drawn against Davison's original design. The SGTR is a simple, data-driven, and minimal-order LTI controller that solves the error feedback output regulation problem for stable LTI systems. It is based on samples of the open-loop frequency response, offering a guaranteed stability margin. The design steps for the SGTR are outlined, including pole placement and computation of the feedback gains F. A simulation result for the 4-tank process demonstrates that the SGTR outperforms Davison's design in terms of disturbance rejection and error trajectories. The closed-loop system eigenvalues are presented, showing that the dominant eigenvalue with the SGTR is further to the left in the complex plane, indicating better stability. Future work directions include extensions to the case of repeated exosystem poles and unknown exosystems, incorporation of feedforward and proportional derivative action, connections to more recent advances in data-driven control based on behavioral systems theory, discrete time versions of the results, and applications in renewable energy integration problems. Adaptive control algorithms for uncertain linear systems is a pressing challenge in control theory. This paper presents a comprehensive analysis of novel adaptive control algorithms, focusing on low-gain stabilizability, integral control, and adaptive regulation in multivariable systems. Low-gain stabilizability is crucial for designing controllers that can handle unknown or uncertain system parameters. The authors provide necessary and sufficient conditions for low-gain stabilizability, enabling the development of robust controllers. Integral control eliminates steady-state errors in the system's response by using an adaptive internal model to track and reject disturbances. This approach is essential for achieving robustness in the presence of uncertainties. Adaptive regulation involves adjusting control parameters based on real-time measurements of the system's state, making it particularly useful for systems with unknown parameters. Techniques such as model reference adaptive control and adaptive internal model control can achieve adaptive regulation. The paper's theoretical developments have practical implications for controlling power systems and designing decentralized controllers for large-scale systems. The proposed adaptive control algorithms can improve the stability and performance of these complex systems. Future research directions include developing more efficient algorithms for adaptive control and extending the proposed methods to nonlinear systems. This paper provides a thorough exploration of adaptive control techniques for uncertain linear systems, offering insights into the theoretical foundations and practical applications of these methods.